let's go ahead and get started. I'm going to share my screen with you. Okay, and hopefully you all can see that shared screen. If you cannot, please let me know. And so let's go ahead and get started. Right. Back up one slide, sorry. We're going to talk about regulatory issues and hot lab quality control. And the Nuclear Regulatory Commission rules are all published and updated at least annually in a series of volumes called the Code of Federal Regulations. We often see it as CFR, and it's a whole shelf full of books. Volume 10 is the one that deals with radioactivity, among a lot of other things, but all the radiation-related regulations are in volume 10. I'm going to skip the next few slides. These are for the physicians and their training requirements, and they're not applicable to you, so just going to skip a few of those. If you are interested in actually looking at the NRC regulations, these are the URLs. You can see the first one is related to Part 20. That is radiation protection standards. Part 35, which is human use of radioactive materials. So if you ever want to see word for word what it looks like, that's where to look it up. Also, I have done a lot of cutting and pasting from those regulations. So you're going to see exactly what's in the CFR pretty shortly. So the first 2/3 of today's class will be on the radiation safety rules and regulations, and the last third will be on hot lab quality control. Now, normally when you get an exam question, you're not going to get 10 choices like you have here. There are only going to be 4, but I've put a lot of choices here for a specific reason just for this question. How do we define an unrestricted area? That would be the conference room, the reading room, the secretarial space, hallways, those kinds of areas where we're not ever allowed to bring radioactive materials. That's an unrestricted area. What is the rule? There are 2 numbers you need to know. One of the numbers is reflected in this slide. But the big question is the reading what you see on the left over here? Is it MR per hour? That would be an instantaneous reading that we got with a Geiger counter. Or will it be on the right? Sorry. Or will it be what's on the right? That is millirems in 1 hour. That's an integrated dose over time. We're wearing a film badge or more likely a pocket dosimeter to measure that dose. So first of all, what do you think the reading will be? MR per hour, instantaneous, or an integrated dose over time? What do you think?
Integrated dose over time.
Perfect. And many books, not many, but some books have the wrong answer for this question because they will say that it's the one on the left, MR per hour. It is not. What's the correct number for an unrestricted area? Anybody?
2.
Good. So here's the rule. Now this is a copy and paste job right out of the CFR. Part 20, that's protection standards. Each licensee shall conduct operations so that, look at the second bulleted point, the dose in an unrestricted area must not exceed 2 millirems in 1 hour. And the other limit is 100 millirems for members of the general public. That's members of our families who are not radiation workers are permitted 0.1 rem of what we would refer to as occupational exposure. Let me give you an example. You're a newspaper reporter. You went to a nuclear power plant for a 2-week visit to write a report. That's an occupational exposure. And so that limit is 100 millirems per year for anyone in the general public. Does that limit of 100 millirems include medical radiation? Yes or no? So the answer is it does not. Almost any scan that you have would blow that limit right out of the water. A CT scan would be several thousand milligrams of local dose. So the limits are 2 MR in 1 hour and 0.1 rem or 100 milligrams in 1 year. Now, there are some general radiation safety rules that are pretty logical and intuitive. We already know what they are. You're not allowed to drink or smoke or store food in the hot lab refrigerator. Those are the general rules. And then the state of wherever you work, if you're an agreement state or the NRC, will provide you with rules and regulations. And we want to have those posted. So this is a common sense question. What should we post? 1, 2, or both, or neither? I think it's probably pretty logical that we need to post both of those. Okay. Now, here's one of my favorites. The general rules: no mouth pipetting of radioactive materials. That is one of the dumbest things I can think of, and yet I have seen scientists do that. All it takes is about 10 milliseconds of not paying attention, and you've got a mouthful of something you don't want. So that's a really bad idea. So all of these charts, especially the ones provided by regulators, have to be posted in your laboratory somewhere. This is my boss, Dr. Robert Wagner, and one of our quite pregnant technologists. The picture was actually taken a number of years ago, and she is saying to him, good morning, I'm informing you that I'm pregnant. The estimated date of conception is some point in time. And of course, he says, congratulations. So here's your question. What happened was she gave him the 2 required pieces of information, but she gave it to him verbally. So here's your board question. Is she legally considered a declared pregnant worker? That's a subcategory of occupationally exposed individual. So is she legally a declared pregnant worker or not?
No.
No.
Definitely not, because it must be in writing. And here is the proof. This is section 1208 on to part 20. And look at the very first thing. The limits apply to the embryo fetus. We're assuming that the mom's radiation absorbed dose is equal to the fetal dose. We're not too worried about the mom. We're worried about the fetus when she's working. And so she has to formally notify her employer in writing. And once he or she has accepted that, she is then going to have a reduction in her maximum permissible dose from 5,000 milligrams per year to 0.5 rem or 500 milligrams during her pregnancy. That's why we ask her, when did you get pregnant? We go back and look at film badge readings from that point in time forward. We add up everything. At the time she announces, we subtract that number from 500, and that's what she's got left for the remainder of the 9 months. Also, look at the second bulleted point. We're expecting that she's going to pick up a relatively constant value of perhaps 20 or 30 milligrams per month. We don't expect 250 milligrams yesterday and 250 today, and she's done. We don't expect that. We don't want that. That's the last thing we want. It should be a very slow, cumulative, but chronic kind of dose. Now, you are very likely to get the next several questions or parts of them on your board examination. If you see the term MPD, that refers to the maximum permissible dose. And there are 4 of these that you need to know. There is your whole body dose, your extremities, meaning your hands, internal organs, and your eye dose. So let's take a look at what they are. This first question says, what is your MPD whole body and that of the declared pregnant worker, respectively? So what is our MPD whole body? How many milligrams?
5,000.
5,000. The pregnant lady is 500. So the third choice down would be the correct answer, 5,500. How about this one? Your whole body dose and your hand dose but now I've changed the units from millirems to rems. Which choice do you like? 1, 2, 3, or 4?
2.
1.
2 and 1. Okay. Personally, I like 1 a lot better because your whole body dose would be 5 rems or 5,000 millirems. Your hands are permitted 10 times that much or 50 rems, mainly because there's no bone marrow in your hands to speak of, and you're not at much risk of getting a pretty high hand dose. Nevertheless, we don't want anyone near 50 rems. Even radiologists who have their hands in fluoro beams have the same limits, and they're much more likely to get a higher dose than we will. Okay, so that's choice 1, 5 rems and 50 millirems. How about this one? What is your MPD for your eyes for 1 year? Anyone?
15.
Good. 15 rems. Now, I've known this limit for many, many years, and it doesn't make any sense to me because, number one, we don't routinely measure eye dose. In fact, we don't even have a way to do it. I mean, nobody walks around with a film badge clipped to their eyebrows. You know, there's no good way to measure that at all. Nevertheless, there is a limit, and you need to know it. And the correct answer is, of course, 15. Now, the other thing that you need to do is to be able to convert all of these into millisieverts. Unfortunately, you have to know both systems, the millirems, the millisieverts. The fortunate thing is that the conversion factor is very simple. You're going to take the number of rems and divide by 100 to get sieverts. You're going to take the number of millirems and divide by 100 to get millisieverts. You're going to take the number of microrems and divide by 100 to get microsieverts. So you want to make sure that the prefix milli or micro, but usually milli, is going to be the same. So let's take a look at the first one here. 5 rems is 5,000 millirems. How many millisieverts would that be? Right?
50.
Good, 50. 5,000 divided by 100 is 50. 50 rems for your internal organ dose or your hand dose. How many millisieverts would that be?
500.
Good. That's 50,000 divided by 100 is 500. The lens of the eye is 15, so that would be
150.
150, and then the extremities down on the bottom is 50. So that would also be 500. Okay, great. There are your answers to those. Let's say that you've picked up 2,200 millirems in the first 6 months of this year. It's now July 1st, you're changing jobs. True or false? You will be permitted 5,000 additional millirems for the remainder of the calendar year.
False.
Totally false. No one cares how many jobs you have. Your limit is 5,000, whether you have 1 job or 5 jobs, makes no difference. So totally false. And this just says that you have to reduce the total permissible by whatever you picked up when you changed jobs. How often must your employer inform you of your cumulative radiation exposure? Now, I'm not asking you how often it's routinely done, because I think everybody knows that film badge reports are published and posted on the wall every month. So it's done typically monthly, but that's not the question. The question is, from a legal standpoint, how often must your employer inform you? Anybody want to take a guess? Is it monthly, quarterly, semi-annually, or annually?
Quarterly. Annually.
Great. It is an annual requirement, and they're meeting that requirement times 12 by posting it every month. So no one ever violates that law, ever. So it's routinely done monthly, but must be on an annual basis. Okay. Let's say you came in this morning, 7 a.m., and checked your dose calibrator. It's working fine. Now, if you are called in at 12:15 tomorrow morning, that's a little over 17 hours. You're going to do, let's say, a stat lung scan. It's already the next day. What is the requirement for repeating the dose calibrator test? The real question here is it every 24 hours or is it every calendar day?
Every calendar day.
Good, it is every calendar day. And so here's what happens. If you draw a dose at 11:55 p.m., you're good. If it's 12:01 a.m. or later, you got to repeat the constancy test, at least on the isotopes that you're going to use. So you come in for a stat lung scan, you're probably going to check both technetium and xenon if you're a xenon user, but it's every calendar day. And that day starts at 12:01 a.m. And so that's something to remember. This smoke test, I don't know if you've ever heard of this or not, but the state or the NRC inspector comes in and says, where do you do ventilation studies? You point out the room, he closes the door, he's out in the hallway. He has what's called a smoke gun, and he blows a puff of smoke under the door. Now, what should happen to that puff of smoke? Should it go under the door and into the room? Should it be blown back out in the hallway? What should happen to it?
Should go under the door.
Okay, what's the requirement? What's the pressure requirement?
Negative pressure.
I don't know, less than the hallway.
Yeah, correct, exactly. So negative pressure means that the pressure in the room is lower than what's in the hallway. And the reason it would be lower is that every room has a ventilation system, which is constantly exchanging the air. And so this test, by the way, is no longer mandatory. The inspectors don't ever do this anymore. It almost never failed anyway. If you want to do it, you certainly do so. So again, no longer required. What does ALARA stand for?
As low as reasonably achievable.
Good. So here's where it came from. In section part 20, Radiation Protection Standards, subsection 1101, every licensee, this is the exact wording, shall use to the extent practicable procedures and engineering controls to ensure that doses are as low as reasonably achievable. That's where that came from. Now, who was the ALARA policy designed to protect? Technologists or patients or both?
It's both.
Actually, it was designed for technologists. There's not much you can do to keep doses of ALARA for patients other than reducing the prescribed dose, which we really don't want to do. So this was an effort that started in 1975 to enhance technologists' awareness of radiation safety. And it said things like, always keep every bit of radioactivity and lead 100% of the time, except for those brief moments when you have no choice but to take it out. It just heightened the awareness of technologists. In 1996, I believe it is, it became a mandatory policy for all nuclear medicine departments. You have to have an ALARA policy in your policy and procedure manual. So the best correct answer here is, of course, the technologist. And here's another exam question. You have to have, every department has a radiation safety program implemented by the RSO, and also an ALARA policy also implemented by the RSO. And according to federal law, these are not just programs and policies, but they are documents that have to be in your policy and procedure manual. And they have to be reviewed. Whose job is it to review the radiation safety program and the ALARA policy? And how often?
The radiation safety officer, and at least once a year?
Good. The RSO has to do it, and it must be done at least annually. You can do it more often if you would like to. And in fact, some very, very small programs, like maybe an imaging center that only does cardiac studies and they only have one technologist, one doctor, they usually have a consulting RSO who comes in quarterly checks out their program and annually checks out the LR policy and the paperwork just to make everything is in order. So this is where it came from. Every licensee shall periodically, at least annually, review the safety program, and on the very bottom line, the LR program. And it says here that usually it's the RSO or his designate, which could be a consultant, could be the assistant RSO, but someone who is competent to do that review. Okay. You are permitted to designate one sink in your hot lab as a, you'll note in quotes, a hot sink. You are permitted to dump down that hot sink microcurie activities of any isotope you want. You should then flush it with lots and lots of water and get it far away from you and way down the pipes. There's a requirement to log in every one of these these dumpings into the hot sink. It would be something like 10 microcuries, technetium-99m, time, date, and your initials. And on December the 31st at 5 p.m., the RSO is supposed to collect all the hot sink logbooks, add up all those microcuries, and pray that it does not exceed the institutional limit. So what is that institutional limit? Now, it's a limit for all users on all isotopes under one license. What's the limit?
1 curie.
Good. 1 curie per year for all isotopes for all users. There are 2 exceptions to the rule, but they're not medically valuable for imaging, and I'm not even going to confuse you with what they are. So the correct answer is 1 curie per year. And just a couple of provisions here. What you dump must be water soluble. In other words, you can't dump radioactive iron filings down the hot sink because they're not going to leave the trap underneath. They'll be there forever. So it has to be water soluble. It could be biological material like plasma or urine or something like that. And we have to document every single disposal. And as you see in the bottom bullet point, total quantity for the whole institution, 1 curie per year. Okay, great. This I think we've covered a couple of times. All administered doses must be within what percent of the prescribed dose?
20.
20%. Does the route of administration make any difference at all? Does it? Not at
No.
all. It doesn't matter if it's injected or oral or some other route. It makes no difference whatsoever. Now, we used to live with the famous 10% rule, and some hospitals, including mine, still do. We don't like the 20% rule, and we have set our hot lab computer as a default for 10%. And so if someone enters a number not within 10% of the prescribed dose, a big red box shows up and says, go back and modify the dose that's out of the limits. But that's not the law. That's what we chose to do. The law is always going to be plus or minus 20%. Now, if you are outside of that 20%, that is an event. That does not tell you yet whether it's a recordable or a reportable event, but it will be an event. And is a dose that's too low as bad an event as a dose that's too high? And the answer, believe it or not, is yes, it is. If you are outside that plus or minus 20%, they're equally bad. If it's too low, you can fix it by injecting more. If it's too high, nothing you can do to fix that. Can't go back in and take some out. Here's a technologist who's saying to the physician, you know, I have a 400-pound patient coming in for a bone scan. Our typical dose is 25 millicuries, but I think it would be a good idea to give 35 millicurie dose. And the doctor says, okay, sounds like a good idea, go ahead. We'll go ahead and do that. So technologists gave him a recommendation. The physicians gave a verbal approval. Again, does that verbal consent meet regulatory requirements for modification of a dose? And I see some head shaking no, and that is, of course, the correct answer. It must be in writing. Some departments have a big rubber stamp. Bam, they stamp it. It says, prescribed dose modified to blank millicuries by blank on this time, this date, and the doctor has to sign it. The only time a verbal is okay is like in an emergent situation where, let's say it's a child or a demented patient who can't give consent to proceed. You can take a telephone consent, but you have to have two people on the phone and they have to sign that they were witnesses to the conversation. So it must be in writing. Now, let's probe a little bit into whether something is a reportable or a recordable event. Here's the case where, let's say we had bad handwriting. The doctor wrote down 3 millicuries. The technologist thought the 3 was a 5 and gave a 5 millicurie dose of thallium. Now, that's a 67% overdose. Pretty obvious that that's a violation of the law. It's certainly an event. But the question is it recordable or reportable? And so we have no way of knowing until we look at the internal radiation dose. And so here's your information. No internal organ picked up over 15 rems. That's 15 rems. And the whole body dose was 2 rems. So violation of the law, yes. But was this reportable or recordable?
Reportable?
Recordable. Now, good. Now, here's how you know that the numbers that go with recordable are identical to your MPDs. Take a look. Look on the very bottom. If the whole body dose is less than 5 rems, that's your MPD whole body for the year, and no single organ picked up 50 rems, that's your MPD for the year, then that, as bad as it might sound, that is still a recordable event and not a reportable event. However, if either one of those was exceeded, if either the whole body dose was greater than 5 or a single organ dose was greater than 50, that would be reportable. Now, what are some of the other things that constitute an event? Let's just review. There are basically 3 of them. Wrong dose, not within plus or minus 20%. The wrong route, you were told to give it intravenously. You can't find a vein, but very conveniently, there's an arterial line in place. You're not allowed to do that. That's a violation of the law. Or the patient got the wrong drug. So that's the first thing, incorrect radiopharmaceutical. That should never happen, but unfortunately, it does periodically. I've seen it happen. I've seen it where they had the right patient, and they went into the hot lab and to get MDP, and somebody handed them a DTPA dose. That's just bad practice of medicine, basically. Now, what happens if you have a reportable event? Well, you have to write up an incident report, document the details. One of the things you never do is identify the patient. The NRC, the state, they don't want to know who the patient is. They don't want that kind of personal information. But there are 2 things. They want you to write up what happened. And most important of all, look at the last sentence. They want to know what you are going to do to make sure this never happens again. I want to mention some events that I've seen over the years, and every one of these is totally preventable. We had a technologist walked into the waiting room and said, "Mr. John Walker." A guy raises his hand, says, "All right, sir, hold out your arm," gives the guy an injection. It turned out it was a patient who had been delayed. He answered to somebody else's name, so somebody would do something to him so he could go back up to his room for lunch. Now, whose fault was that? Patient or the technologist?
Technologist.
Of course it was. He didn't identify the patient. He didn't say, "What's your name?" Not a year later, we had a technologist walk in the waiting room, "Mr. John Walker, right here. Let me see your wristband, John Walker. All right, here goes your dose." We unfortunately had 2 John Walkers at the same time, but for different studies, meaning different pharmaceuticals. And we had a 50-50 chance of getting it right, but you all know what Murphy's Law is. And so we injected the wrong patient. Those things happen. They shouldn't happen, but unfortunately they do. Now, all of the rules and regulations we covered so far for prescribed doses and reportable and recordable events in particular, do not have anything to do with therapy doses. The rule for therapy is that if you're not within 20%, that is a reportable event. That would not be the case diagnostically, but let's take a look here, for example. The patient was treated with sodium iodide for hyperthyroidism. The actual dose was 17% higher than the prescribed dose. Was that recordable or reportable? Now, for therapy, it should be within 10%. So 17% is too high, but is that a reportable event? And the answer is no. If it didn't exceed 20% in either direction, plus or minus, that is a recordable, but not a reportable event. So for therapeutic, an administered dose not within 20% is reportable. However, to it is that if you give a therapeutic and you recognize that the dose is too low, you could always give more and get it back into the prescribed dose range. But if it's too much, you're out of luck. The other thing is that if a therapy dose is administered to the wrong patient or by the incorrect route, that of course would be totally a reportable event. Okay, let's say that you are the dose administrator. You gave a 150 millicurie therapy dose of sodium iodide 131 to a patient who has thyroid cancer. Which of the following is required by the NRC for the person performing the dose administration? Now, considering that I happen to know the answer to this, I am praying you do not get this question on your exam, because a lot of people don't know what the current regulation is. In fact, up until November 2006, the first choice was correct. Thyroid count at 24 to 72 hours post-administration. We always did it at 24 hours for the dose administrator. That's what it used to be. Now, it's actually none of those. And in fact, there is a very vague statement in the regulations saying timely monitoring of the radiation dose of the dose administrator. I don't even know what timely monitoring means. It doesn't tell you, is it 24 hours? Is it 72? Is it a week? Is it 2 weeks? How do you monitor it? What do you count with? How long do you count? There's no guidance whatsoever. So what people routinely do is they check the thyroid of the dose administrator 24 to 72 hours with a special probe calibrated for iodine 131. Technetium probe will not be appropriate at all. So that's, I just hope you don't get that question, because the correct answer is it's no longer really specified in the regulations. Every one of us who lives at sea level picks up about 300 to 350 millirems per year. That is our background radiation. Before we tackle this question, is medical radiation included in your background radiation? Yes or no?
No.
Correct. It is not. You could be at very high levels, way above background, with just 1 or 2 scans. So that is not included. So out of that list of 6, which 3 of those are the most significant source, and which one of them is by far the most significant source? So let's go down the list and just say yes or no. It's a contributor to our background. Cosmic rays.
Yes.
Yes.
Yes, we are being bombarded with them right now. They go right through the building and through you and through everything. Flying in airplanes.
No.
That's correct. Half the people in this country have never been on an airplane because they can't afford to do so or are afraid to fly. And in fact, flying from New York to London, a 3,000-mile trip, is only about 5 or 6 millirems. It's half of a chest X-ray. It's a very tiny amount. Global fallout.
No.
No, no one has blown up a bomb in the atmosphere since 1955. Global fallout is essentially 0. How about internal radioactivity? Are you radioactive?
Yes.
Yes, you are. All of us are. We have 2 isotopes in our body, and those are potassium-40, which has a half-life of over 1 billion years, And so we don't worry about that because in our lifetime, there are not going to be enough decays to be of any concern. The other is carbon-14, which has a 5,760-year half-life. And that's also so long compared to human lifetime that it's going to be insignificant. How about nuclear power plants?
No.
No. They estimate that the average American picks up 0.3 of 1 milligram. That's almost indistinguishable from zero because there are nuclear power plants. The only people at risk are those that might live within 1 mile of it. And even they are not really at much risk because the containment vessel for the nuclear reactor always is under negative pressure. And so it cannot escape into the atmosphere. So those are the three most important ones. Which one of those, or we didn't cover the last one, radon and terrestrial sources. That's certainly a yes. And out of those three, which is the highest?
Would it be the terrestrial sources?
Yeah, well, yes, it would be radon and other terrestrial sources, correct. Radon is thought to confer over half of our background burden, background radiation dose, radon alone, and other terrestrial sources. And there are radioactive materials that are natural things that people don't know about. We have a person in our family who has a vacation home in upstate New York who bought a beautiful piece of red granite and had it installed in her kitchen. A one-of-a-kind piece. Turned out that the radon inspector came around, checked her property all around, came into the house, said everything looks great, set his Geiger counter down on this red countertop, and it started singing. It turned out that those red streaks were uranium, and she became terrified and had the countertop removed and in exchange for one that did not have red in it. So there are sources of background other than just radon that we have to deal with, but most of them are very tiny. Also, smoke detectors have a very tiny amount of americium in them, but it's an alpha emitter and it doesn't penetrate at all, so they're very safe to handle. How does the NRC define an adult? What age?
18.
18, great. It's interesting, by the way, that the NRC has a weird rule. If you're under 18 years of age, there is a limit of, I think it's 500 milligrams. However, you're not allowed to work in radiation if you're under 18 years of age. So I don't understand why there's a limit, because you're not allowed to hire anybody that's under 18, but there is. So it's 18 years of age. Now, there are signs, you've all seen the signs in your lab that say caution radiation area. That's what we typically have in nuclear medicine. It's very unusual to see a sign that says high radiation area. You might see that in a radiation therapy department. And then there's a sign that says very high radiation area, grave danger. That is a nuclear power plant sign. You'll never see that anywhere else. So let's review what the numbers are associated with those areas. A radiation area is one where you could pick up a dose of X milligrams in 1 hour. Now note, that's an integrated dose over 1 hour. It is not an instantaneous reading of X MR per hour. That's a cumulative dose measured over 1 hour and at a distance of 30 centimeters. So X is going to be for a radiation area and Y is going to be for a high radiation area. And obviously there are different numbers. Let's go back. Anybody know what X is for a radiation area?
5.
It is 5, good. And how about a high radiation area? Okay. Want to take a stab at it? So that one is 100. And here are the answers to those. The first one, radiation areas, it says 0.005 of rem, that's 0.5 millirem. And if it's 0.5 millirem, at 0.5 milligram, we divide by 100, we get 0.05 of the millisievert. The high radiation area says it's 0.1 rem, that's 100 milligrams. And the very high radiation area, it says you can pick up a dose of over 500 rems in 1 hour. Now, that's for someone who, in case of an emergency, has to go into the reactor core. You can pick up a lethal dose in 30 seconds if you're in the reactor core area. It has to be a catastrophic situation for anyone to even consider going in there. Let's take a look at what lethal doses are. I don't know if you've ever seen this terminology before, but there's a term called the LD 130. That means what is the lethal dose where 100% of the people would die within 30 days as an acute dose delivered all at one time, let's say within 1 hour. And what is the LD 50-30? This is the lethal dose where 50% of the people would die within 30 days, and the other 50% probably would wish they're dead because the radiation sickness that evolves is so terrible with unrelenting nausea and vomiting and diarrhea and other nervous system problems. It's really just awful. So what are those numbers for the LD 100, LD 50? And here they are. These are not likely exam questions, by the way, but you never know. So the LD 100 is about 550 rems, whole body. And the LD 50, where half the people would die, is about 350. Now keep in mind, this is for an acute dose all at one time. This is not a chronic dose. There are two places in the world where the annual background radiation is something like, I don't remember what the number is, 5 rems per year background. So that, if you live 70 years, you picked up 350 rems, but that's a chronic dose and not an acute dose. And in fact, the people who have that very high background rate have no higher cancer rate than anywhere else in the world. Now, at the bottom, it says, with very high level medical intervention, it's possible to raise the LD 130 up to around 800 or 850 rems. Beyond that, no one can save your life, no matter what they do. It's interesting scientifically that small animals like roaches and mice and creatures like that can pick up 1,000 rems and nothing whatsoever happens to them at all. They're not immune to it, but they're just much less sensitive to radiation than humans are. Now, here's another one of those questions with a percent on it. And in a moment, I'm going to give you a rule that will solve a lot of your problems. An individual must be monitored for radiation dose with a film badge if it's likely that he's going to pick up what percent of the MPD. Remember, the MPD is 5,000 per year, whole body. So if you have a visitor to your lab, and let's say he's going to be there for 6 months, and you feel that he's going to pick up more than a certain number or a certain percentage, you have to monitor him. What's that percentage of the MPD?
10%.
Good. So here's a rule for you. Anybody asks you about a percent, the answer is always going to be 10%, always, with the sole exception of prescribed doses and administered doses. Everything else is 10%. There are 4 dose calibrator tests. What's the limit? 10% for all of them. So if you don't know, go for 10%. Now, here's where that rule came from. We're still working in part 20, radiation protection standards. If someone is likely, in your good medical judgment, to receive more than 500 milligrams per year, you have to badge him. If you think it's less, you don't. It's better to badge him and not take a chance, truly. What kind of radioactive materials license does the hospital have where you do your training? Specific or general or broad?
Broad.
Good. A broad license is a license that lets a hospital use any isotope of any element in the periodic table for any reasonable purpose, for any reasonable quantity. There are what are called possession limits. For example, your license probably says, yes, you can use thallium, but no, you can't possess more than 50 millicuries at a time. There's no reason to. You know, you can't go and order 500 millicuries because there is a possession limit. So a broad license lets almost anybody do anything, but it's under the care of a professional RSO and board certified nuclear physicians or radiologists who are authorized users on a license. Specific license would be the case where, let's say, someone runs a small nuclear cardiology imaging center. That's all they do, cardiology, MUGAs and stress rest cardiac studies and maybe FDG, cardiac PET, those kinds of things. That would be a specific license. Someone walked in there and said, hey, I need a bone scan, and the nearest other hospital is 50 miles away. You can say, sorry, not allowed to do it. It's a condition of our license, can only do cardiac. And a general license is the lowest level license there is. This lets you use microcurie amounts where basically you're going to be pipetting things like in a radioimmunoassay, but you're not going to be injecting patients. So here's the definition of those several licenses. Basically, all hospitals have broad licenses. A GM survey of your lab and a wipe test must be performed how often? Now, those two are unrelated. You know, a Geiger counter survey of your lab and a wipe test, they're totally unrelated, but they happen to have the same answer to this. But they have fairly similar time intervals, but they're not really the same. So how often? Daily and daily, daily and weekly, weekly and daily.
Daily, weekly.
Good. Totally correct. Daily and weekly. You have to do a GM survey of every room every day where isotopes are used. You do not have to go survey the conference room or the reading room unless there's a likelihood of a spill. You don't have to. But every imaging room, the hot lab, always has to be checked every day. And the wipe test is every week. What's the most appropriate day to do the wipe test, Monday or Friday?
Friday.
Friday is certainly the most appropriate day. Monday would be the best day to do it because you're not going to find anything because you probably spilled technetium and that was 60 hours or 48 hours before, and you've gone through 8 or 10 half-lives, so you won't find anything. But Friday, you should be doing it at the end of the week. Now, the GM survey, and this just has the answers daily and weekly. The GM survey, they want you to record which Geiger-Müller counter you use, what's the make, model, serial number, what units are you reading? Are there going to be counts per minute, disintegrations per minute, MR per hour? And most important, they want an action level. When are you going to clean up a spill? And you might say, okay, my action level is going to be 50, let's say 50 counts per minute. If it's higher than that, I'll clean it up. If it's lower, I won't bother. I don't know. I don't think that's actually a good action level. I'm not sure what it should be, but you have to have one that meets radiation safety standards. And RSO would know what that number is. I just am not sure what it is, but you have to have an action level. Now, the wipe test, you have to draw an accurate area map for every single room in your department where isotopes are used. And then you're going to take 5 to 7 dry wipes. You need that area map. You're going to print many copies of it, and you mark on the map where you took wipes 1, 2, 3, 4, 5, 6, 7. And then you're going to correlate the count rates for those 7 samples with the locations on the map. Now, if everything is background, you take the printout from your counter, clip it to the area map, and you're done. You're done for the week. But if you have a hot spot, then that's a problem. We'll talk about that momentarily. So here's what an area map might look like. You can see there's a sink, injection table, several countertops. There, of course, is the door. There might be a camera there. So we've taken, I don't know, 6 or 7 or 8 wipes here. Let's say spot number 5 is 100,000 counts per minute. Everything else checks out just fine. But spot number 5 is really hot. So what are our first steps? First thing we're going to do is to tell everybody, okay, don't come in this room. There's a hot spot on the floor. We don't want to track it all over the place. And I'm going to decontaminate it. Okay, so now we've secured the area. What are the next 3 steps? What are we going to do to that spot? What's the first thing we're going to do? So the first step is
do a survey to population.
First thing we're going to do is to decontaminate it. Then what do we do? We have to recheck it to make sure it's decontaminated. And then what do? We log into the logbook, the area map logbook, the before and the after readings. The inspectors don't care. They don't, let me Mark, go ahead a little bit. The inspectors don't care if you have a hot spot. I mean, they don't want it every day, but if you have an occasional hot spot, they really don't care. But your obligation is to document that hot spot, decontaminate the background, and record the new reading. All the inspectors want to see is the before and the after readings. I found this cute little boy on the internet, and the way the inspectors look at it is that the job is not complete until the paperwork is done. If you've ever been through an inspection, they love looking at the paperwork because that's their way to make sure that you are in compliance with all of the federal laws. Let me back up a little bit here. Okay. What energy window would you use when you're counting wipe tests? Would you use 140 plus or minus 20? That would be great if you don't use any isotope and technetium, that would be totally appropriate. But what if you use other things? Maybe use gallium and thallium and indium and who knows what else, iodine. So what energy window should we use?
It's an open window.
Good, so they often call that an open window, but what we want to do is make sure that it at least goes from 50 keV up to about 400. Our lowest energy thing is thallium at 71. Our highest energy is iodine at 365. So if you run from say 50 to 400, that's good. But you can also use an open window. But when you do that, you also have to count your background in that same window. What is the only commonly used isotope you will never ever find on a wipe test? That's right off an old exam, by the way.
Xenon.
Xenon. You'll never find a gas on a wipe test. It won't stick to a wipe. You'll never find it. And you'll see shortly that when you receive a box containing xenon, if that's all that's in there is xenon, you don't even have to wipe test that box like you do for everything else. Okay. So this we already covered. How about sealed sources? First of all, what are a couple of examples of sealed sources? And then how often must we leak test our sealed sources? So first of all, what are some examples of sealed sources?
Markers.
Good. Spot markers. What else?
Your cesium source for your QC testing.
Good. Cesium source. How about dose calibrator check sources, where we use cesium and cobalt 57 and cobalt 60, low, medium, and high energy. All those dose calibrator check sources are sealed sources. And what about physically the largest one of all? It might be a very large rectangle or a very large circle.
Your flood source.
Sure. So our cobalt 57 flood sources, they're sealed. They are made by taking liquid lucite, which is homogeneously filled with cobalt 57. They pour it into a mold. They let it freeze or harden, hard as a brick. And then that source is literally hermetically sealed inside of this very, very tough plastic. So you can pick that source up and touch it all you want. You'll never get contaminated. You'll get a radiation dose. You'll never get your hands contaminated because it is totally a sealed source. And in fact, If any sealed source is ever leaking, the appropriate action is to take it and return it to the manufacturer, because if it's leaking once, it's leaking forever. You have to return it. Now, here's your exam question. How often must you perform leak testing on sealed sources? Is it quarterly, semi-annually, annually, or monthly?
Semi-annually, 6 months.
Good. That's the only thing we do semi-annually, and is leak testing every 6 months. And this lists some of the sealed sources here. Calibration source, dose calibrator, spot markers, all those have to be checked. Okay, how would you define an agreement state? So I'm going to define it for you. An agreement state is a state that has signed an agreement with the federal government, with the NRC, stating that the state will do all of the regulating and all of the inspecting, but will follow the NRC guidelines. Now, the NRC guidelines are going to be the threshold. Which may be more restrictive than the other, NRC or the agreement state? Everybody? And the answer is, of course, the agreement state. They have to follow at a minimum the NRC guidelines, but they could choose to be more restrictive. For example, in my department, our prescribed dose rule is 10%. We've chosen to be more restrictive. That's perfectly okay. It's not okay to be more lenient, but it's okay to be more restrictive. And so, do all of you know whether your state's an agreement state or not? And if not, you're going to know in about 10 seconds when I show you the map. But approximately 39 states plus Washington, D.C. Are agreement states, and the rest are NRC. VA and military hospitals, that's federal. Here's a pretty current map. And you can take a look and see. I know there are Texas people here. There's some people from Connecticut. Connecticut's an NRC state. There are Florida people. That's an agreement state. Everything that is that orange color is an agreement state. And those ones that are kind of yellowish looking are the NRC states. Also, you'll note Alaska and Hawaii down by the bottom. They are, of course, totally located in the wrong place, but they wanted to put them on the map somewhere. And those are both NRC states. They're not going to ask you, by the way, if your state's an agreement state, but you should know, just in case you ever want to look up the regulations, you want to go to the state website, not the NRC website. I've used the word licensee a bunch of times already today. Who is the licensee? Is it the director of nuclear medicine, who is by far the biggest user of radioactivity on the campus? Or is it the person who is often his boss, the director of radiology? Or perhaps both of them are the licensees? Or is it the institution? Or are individual users licensed? So who is the licensee?
The institution.
Good. It is in fact the institution. Whatever institution you're at has one license. There may be many users, but there's only one license, and that will be the institution. So at my hospital, Loyola University Medical Center has one license. It's a state license. It starts with IL dash some number for Illinois, and that's the licensee. Also, it's possible that if a hospital has one license and they have nearby facilities within just a few miles, that can also fall under that same license. Not if they're 50 or 100 miles away, but if they're pretty close, it could all be under one license. Now, these two, again, have nothing to do with each other, but they have the same answer to this question. Hand monitoring, all technologists monitor their hands, sometimes frequently. Treadmill monitoring, what is required? How often must they be monitored?
Daily.
Daily. Now, most technologists monitor their hands at least twice daily before they go to lunch, so they make sure they don't contaminate their tuna fish sandwich, and at the end of the day. And so daily is the answer, although from a practical standpoint, it's usually more often than that for monitoring the hands. And What the inspectors want to know is they don't care if the record shows that you had a hot hand. They want to see the before and the after reading. So if you have a hot hand and say, oh, I got a Geiger counter in my hand, I measured 5,000 counts per minute, I got some cleaner and cleaned my hands up, and now it's down to 20 counts per minute. You record those two numbers and everybody is happy. But if you record that your hands were hot and you did not show the after reading, according to the inspector, you didn't do it. You can't say, yes, sir, I monitored my hands, I forgot to write it down. You're just asking for a citation. So please be aware that if your hands are hot, you should be recording before and after readings in some standard unit like MR per hour or counts per minute or something of that kind. Also, the treadmill. It's very, very difficult to decontaminate a treadmill. I'm not sure why, but that rubber running surface seems to bind the isotopes and just doesn't want to let it go. And I've seen cases where we could not clean the treadmill well enough and we had to shut it down for overnight just to let it cool up. And in fact, what do we clean our hands with? We have several choices here. There are two solutions. One is called Radiac Wash. One is called IsoClean. They cost about $125 a gallon, and all they are is a little bit of detergent with a little DTPA or EDTA in them to bind up metals. I doubt if it costs them more than $2 a gallon to make it, but pretty expensive. The other alternative is to use something oxidative and abrasive like Ajax Cleanser or Comet or something like that. It's chlorinated, it's oxidative, and it will abrade or remove the surface of the skin on your hand reasonably well and take the isotope with it. Who has to be trained in radiation safety on an annual basis? Let's take a look at this list. I think you'll agree, all of them have to be trained. Nuke Med Techs, our technologists, we've had a very stable staff for way over 20 years, and our technologists have had the same RSO give them the same lecture with the same lecture notes year after year after year. Got to go through the motions, and it has to be recorded. So Nuke Med Techs, all authorized users, the loading dock people, not all of them, but the ones who schlep our generator packages and other packages to us, they have to be trained. Housekeeping, again, not all of them, but the ones who service the imaging rooms and the hot labs. Finally, the security officer, some of them escort a delivery driver, a delivery man down to the department to deposit the generator somewhere. So anyone who comes in, even remote contact with radioisotope, has to have some training. And first thing that inspectors like to ask after they say hello, they walk in your department and say, hello, we're here. They don't usually give you much notice, is show me your training records. And they have to be done. Training has to be done. Initially, that's when you're first hired, and then annually thereafter. Anybody who doesn't keep up their training records is asking for a citation, and there's nothing to it. All the documentation is who gave the training, has to be a qualified person, who gave the training, what was the date, what was covered. That means we take a PowerPoint file, print it up, and we hook it to the list of the names of attendees, and that's all they want to see. They just want proof that you've done it. Paperwork is the key word for the inspectors all the time. You can't just say, I did it and I forgot to write it down. That will never fly. How about this? The NRC inspector has completed his inspection. Let's say you are the director of nuclear medicine. You've been with the inspector all day long. Everything is going great. 5 o'clock, it's winter time. You and the inspector are there, and you're ready to leave for the day. And he says, you know, hold on a minute. Walks over to the hot lab, opens up the door, looks around, shuts the door, takes out his yellow pad. That's always a bad sign. And writes a note on his yellow pad. Did he discover a citable offense or not?
Possibly.
Sorry, say it again.
Possibly.
I need a yes or a no. not a possibly.
Yes.
Yes.
Yeah, sure. This is a security violation, citable offense. It's a breach of security. If he walked in there without your opening the door for him, having to open the door for him, that's a citable offense. If he walked in, anybody could walk in. They could steal therapy solution or generators or any of your isotopes and create, some real havoc. And so that is a breach of security and a citable offense. Now, here's a question that some of the most experienced people that I know get wrong. Must all incoming packages containing radioactivity be wipe tested?
Yes.
No.
Okay, so I heard a yes and a no, and you know what that means. One of you is right.
Not xenon.
Aha, good. So the answer is that the technical answer for that question is no, but the real answer is all of them must be wipe tested with one exception. Look at the bottom line there. A package containing xenon does not have to be wipe tested. If it has xenon and other things in it, let's say you got 3 vials of xenon and 3 MDP doses, you have to inspect it. But if it's only xenon, you don't. So all incoming packages, with the sole exception of xenon, have to be wipe tested. And must they have external readings taken with a Geiger counter? That they should. But for leakage, other than xenon, the answer would be a yes. Now, I don't understand why, but the first bulleted point there about taking possession expeditiously has become a very common exam question. I don't know why. When a package shows up in your department, you have to take possession of it. That means you have to take it in the hot lab and log it in within 3 hours. It does not mean that if someone delivers a package in your hot lab at 2 o'clock in the morning, you don't have to go there and monitor the package. But when you open your department, you have 3 hours to take possession, meaning to log it in and to monitor for contamination. You'll see that the third dashed line down there, packages containing only a gas or special form material. Special form material would be radiation therapy sources. Those do not have to be monitored because therapy sources are hermetically sealed. These are the diamond-shaped labels that you'll see on any package that is delivered to your department. They are called, respectively, a white 1, a yellow 2, and a yellow 3. The yellow 3, the bar 3 label, is only for generators. It has to do with the fact that generators are just screaming hot, and even with the 48 pounds of lead in there, the box reading could be high. So that requires a bar 3. All the pharmaceuticals to receive will have a bar 2 label like the one in the middle, and very, very low level kits like microcuries would probably be a bar 1. So I think I'm going to skip that. Now, when a company sends you a radiopharmaceutical in a box, they, in theory, have monitored that box. They've enclosed a transmittal form telling you what the reading on the box was, and that reading will always be a background reading. If you receive a box, however, and you find contamination, then something has happened. Either they contaminated the box at the company, or maybe someone on your end contaminated the box. But regardless, if you find removable contamination on a package you receive, that is reportable. You have to notify the NRC or the state right away. Because it could be a case of what they call dry labbing, where they just pretended that the box was not hot and put in a background reading and maybe didn't even bother to check it. And the NRC does not like that at all. Okay. Which of the following packages have to be logged into the incoming package logbook? standard of technetium, a dose of gallium, a dose of iodine, dose of chromium, all of those or none of those?
All of them.
Sure.
All of them.
Every single one has to be logged in if it's radioactive. If you ordered a box of heparin or ACD solution, you don't have to log that in. But if it's radioactive, you certainly do. What do you have to log in? So the incoming package logbook used to be done on paper, and it was 2 pages wide because look what has to go into it. You needed the product name, the name, the physical form, the chemical form, like thallium 201 chloride solution, calibrated time, date, the lot number on your end, the activity that you received, and the date and the time, a package identifying number like a FedEx air bill number or a pharmacy prescription number, and your initials. So it's probably 15 or 20 entries that have to go in there. Today, we really do it in the computer, and it's kind of misleading to call it a logbook, but in either case, it's got to be recorded somewhere where the inspectors have access to it. So, and if your license requires you to monitor every package, and almost every license does, then you have to put those numbers somewhere in your logbook. That would be monitoring the package at the surface and at 1 meter. And of course, if you do wipe testing, all that has to be logged in. Now, how do you monitor a package? So every box or every ammo can has basically 6 sides. It's got a top, a bottom, and 4 sides. And the suggested way is to take 1 wipe, wipe all 6 sides, check that wipe. If it's okay, you're done. But if that wipe is hot, then you have to go back and get 6 new wipes, wipe each of the 6 sides separately, find out where the contamination is, put it in a spectrometer and determine what the contaminating isotope is. And then you have to notify the NRC of the state as well as the company that sent you that package. Okay, we're almost at a mental break point here. Which of the following is our acceptable methods of waste disposal? A is transfer to a licensed company or person like a licensed waste hauler, radioactive waste hauler. B is decay and storage. C is releasing of an effluent, that means a gas like xenon gas within authorized limits. All of those or none of those?
All of the above.
All of the above. I copied that. You'll see in a moment. I copied that, pasted it in right out of the regulations. Which of those 3 is the one that we do?
B.
So we do decay and storage. It's prohibitively expensive to transfer a barrel of waste to a licensed company. It costs $500 to $1,000 to have them pick it up and ship it to the state of Washington. And we don't have long-lived isotopes. We would never waste that money on that kind of thing. So instead, we will simply hold it and decay it in storage for 10 or 20 or 30 half-lives, whatever the longest lived isotope is in that bin. And we just do decay and storage. That's what everybody does. So that is the correct answer. And you can see word for word right out of Part 20, subsection 2001. Okay, now let's take a mental break. Any questions about any of those rules and regulations? Anyone? Okay, if you would like to assess your knowledge of the rules and regulations and also Hot Lab QC, one of the tutorials that's on the NUCMED tutorials website is entitled Current NRC Regulations and Hot Lab QC. And it has 50 questions on there. It's a self-grading test. You're welcome to take it at any time. Some of you have already taken it. Actually, I've seen a few people taking it. And it's just a great way to assess your level of knowledge. You might want to wait until you're in proximity to your exam, but it's well worth doing that one. The questions are pretty much the ones I've asked you today, but it'll be a good refresher. Okay, going to take a look now at the, just a second here. at hot lab quality control. If you've ever spent time in the hot lab and had to do quality control, I think you're aware that it's very repetitive, it's boring, it's not interesting, it almost never ever fails the test. And you might be thinking, oh, why do we have to do that? I mean, it's a waste of time and resources and money and so on. And the answer is very clear why you have to do it. It is federal law. And because it's federal law, that automatically makes it state law. And also, from a medical perspective, we want to avoid at all costs a non-diagnostic study. That has nothing going for it. We have to repeat the procedure at no charge. We're going to end up doubling the radiation dose, doubling the patient's discomfort, and delaying the diagnosis. And the worst thing of all, out of all of that, is none of those. The worst thing is that the referring physicians lose confidence in you because you can't even do a bone scan. The way that might happen is you went to do a bone scan and inject a renal agent. You don't even see the bones. And that almost never happens, but in the rare case that it does, it certainly produces a non-diagnostic study. We want to avoid that at all costs. And that's one of the reasons for doing quality control. First day that I was in nuclear medicine, my instructor held up a tuberculin syringe and said, you must be able to say yes to the following question. Would I inject my mother with this drug? And assuming you like good old mom, you better make sure you do some quality control on what's in that syringe. You can't just look at it and say, it looks okay to me. You have to do some testing. And so that's a very good criterion. You want to make sure that what's in that syringe is exactly what it's supposed to be, that it's radio labeled properly in the right radiochemical form, the right activity, and so on. So, according to current NRC regulations, how often must the dose calibrator be checked for accuracy, constancy, linearity, and geometry? Okay. How about accuracy? How often?
Annually.
Annually?
Annually. Okay, good. So we're going to cover each of those individually, but I want to show you what the current NRC regulations are, because to me, it's disappointing. They took this out of the regulations. They used to say you must perform the accuracy test annually, constancy is daily, linearity is quarterly, geometry is at installation, and here's how you do it. Now, look what's in the NRC regulations. We're now working in part 35. That's human use of radioactive materials. Look at B. The licensee, the institution, shall calibrate the dose calibrator in accordance with nationally recognized standards or the manufacturer's instructions. The NRC no longer specifies which tests you have to do. It turns out, of course, that the nationally recognized standards are exactly what the NRC regulations have always been. But the current regulations don't specify what tests even to do. And in fact, if you want to download those nationally recognized standards, you better get out a credit card with a nice line of credit on it, because I wanted to see what they were. And this was about 10 years ago. And I went to the NIST, National Institutes of Standard and Technology. They have those regulations. And it's a 10-page document. And back then, they charged me $90 to download a 10-page PDF file. But I teach this all the time. I had to know what's in the regulations. But that's ridiculous that you have to pay for it. Totally should be free. It's a national standard. So how often do we have to check for accuracy? And the answer, of course, is annually. The way to remember that is AA, accuracy annually. And how do we perform the accuracy test? Now let's back up one step. Yes, accuracy means, did you get the correct answer? But what dose calibrator function are we really checking? We are checking that this calibrator works at low energy, medium energy, and high energy. It does not specify activity whatsoever. All you need is to make sure you have enough activity, like a couple hundred microcuries or more. So you'll note on the slide, cobalt-57, the energy is 122 keV, simulates technetium. Barium and cesium are in the hundreds. I think barium is around 400. Cesium is 662. And cobalt-60 is something like 1.3 million electron volts. So we have a low energy standard, a medium energy standard, and a high energy standard. And we are checking to make sure the calibrator is working properly at all those different energy levels. So the first thing we do is we take out our trusty calculator or a decay chart, and we take the cobalt-57 standard that we buy, we decay correct it to today's date. We do the same for the cesium and the same for cobalt-60. So we know what those three sources should read today. We measure them today. We compare the readings we got with the expected readings. So I'm going to show you an accuracy test, and I would like you to tell me if it's a pass or a fail. Now you'll see on the left-hand column, those are the three isotopes, cobalt, cesium, and the other cobalt. You can see the energies that are listed there. And the calibrated values for today's date are shown in the third column, and our measured values are in the fourth column. So you want to compare column 4, column 3, and make sure that they are within 10% of each other. So look at those numbers and tell me if you think this is a pass or a fail. Remember, they just have to be within 10%. Anybody?
Is it pass?
That's a beautiful pass. Those numbers are within probably 3 or 4%. Look at the first line. If you compare 251 to 248, the difference is 3 parts out of 250. That's 1 part out of 80. That's about 1.25%. The next one is 9 parts out of 330. That's a very small number. The next one is 3 parts out of about 150 something, very small number. All those are within just 1 or 2%. That's a beautiful accuracy test. Again, keep in mind that we are decay correcting those 3 isotopes and putting that number in the third column. Okay. How about the constancy test? How often?
Daily.
Good. So the way I remember it is CC. Constancy test is done constantly or literally every single day. And we have to do it before we start the business day, the constancy test. And we want to take a look at how it's performed. Now, this one is a little confusing for some people. First, we buy a cesium source that has a half-life of 30.2 years. So if we check that source Monday and Tuesday, Wednesday, and Thursday, and Friday, what variation do we expect to see across that week? Big variation, a small variation, or none at all?
None.
What was that, very small? I would say your expectation is the numbers should be totally reproducible from day to day. With a 30-year half-life, how much decay takes place in 1 day out of 30 years? So you're talking about, you know, tens of thousands of days there. So what we expect to see is the same reading across the week, Monday, Tuesday, Wednesday, Thursday, Friday. But now look what we do. We take that cesium source right in the middle of the paragraph. We put the cesium source in the dose calibrator and we read the cesium on the cesium setting. That is a mini accuracy test. We're checking cesium on the cesium setting. Better give the right answer. Then, now here's the important part. We don't touch the source. Leave it in the calibrator, but we change the setting from cesium to, let's say, technetium. We take a reading. Are we going to get the right answer reading cesium on a technetium setting? No. Do we care? No. We want to see the same wrong answer Monday, Tuesday, Wednesday, Thursday, Friday. There cannot be a variation of 10% across that week or your calibrator is failing. And so we check it first on technetium and then on iodine and the other iodine and indium and thallium and gallium and any isotope we're going to use during the day. So here is a constancy test. You can see that for cesium, the readings are all in the 120s, not another 120 reading or even anything near it on the whole chart. But is this a pass or a fail? You just want to read across and look at the constancy of the numbers. Pass or a fail?
Pass.
Totally a pass. Again, a beautiful constancy test. You're lucky to get one that good, but that's what you expect to see. You expect to see the same wrong number. Now, some departments choose Wednesday as like the standard. They compare Monday, Tuesday, Thursday, Friday to Wednesday. It doesn't matter. If Monday to Friday are not within 10%, it's still a fail. So all of those readings have to be within 10%. Okay, good. How often do we have to check for linearity?
Quarterly.
Quarterly. So I was trying to find a good word association for that. You know, AA accuracy, that was nice. I couldn't come up with anything. And a radiology resident a number of years ago pulls a quarter out of his pocket. And he says, you know, if you look at a quarter on edge, it looks linear. And so if that helps you remember it, okay, great. But it is done quarterly. It's the only thing we ever do quarterly is the linearity test. So here's what we do. We take a source of about 300 millicuries of technetium. We measure it at time 0. Let's say it's exactly 300 millicuries, just for the sake of simplicity. Then we decay correct it. What is it going to be in 1 hour, in 2 hours, in 4 hours, in 8 hours, in 24, and 48, 72, 96, 120? You have to take it out until you end up with a reading of down to about 30 microcuries. And so you're going to decay it and read it at all those various points in time, and you're going to compare your reading and the calculated reading that you have done by decay correction. There's also another way to do this, by the way, with it's called the lineator and it's called Kalichek. There are some lead sleeves that fit within each other, and you can do this whole test in 10 minutes instead of in 3 days. But let's say we're doing the 3-day test. So here, time 0, we got 300 millicuries. That's expected and measured. Now, the middle column, we have decay corrected. For example, if you go down to 6 hours on the left, you can see it went from 300 to 150. Another 6 hours, it went from 150 to 75. 24 hours, it went from 75 to 37.5 to 18.25, or whatever that number is. Can't see it on my screen. And then take a look at the measured values. What do you think? Pass or a fail? Anybody? How do those numbers compare? Are they all within 10%?
Pass.
Pass.
Definitely a pass. They're all well within 10%. How about geometry? There are actually 3 times we have to perform a geometry test. Number 1, maybe the most important, is at installation. And if you're ever the chief technologist buying a dose calibrator and it fails the geometry test, my advice to you is give it back and don't buy it. Because if you do buy it, you have to mathematically correct every reading for every volume and every different syringe size, for every different syringe manufacturer, for every different vial size, for every different vial manufacturer. You don't want to mathematically, that's a nightmare. You don't want to mathematically have to correct. So if you can't pass the geometry test or your calibrator can't, give it back, don't buy it. So we have to do it at installation. And what other times would we have to check for the geometry test?
After repair?
Good. After repair, let's say the ionization chamber goes bad, you have to repeat it. And also a significant move. If you move it from one room in your department to the next room, that's not a significant move. But if you put it in your car and bounce it down the road for 100 miles and lend it to one of your buddies, everybody has to do it on both ends, geometry test. So let's take a look at how it's performed. Let's say we're going to take as an example a 10 milliliter syringe. We'll put in 25 millicuries of technetium, put a needle on it, calibrate it, and take a reading. And let's say it's going to be exactly 25 millicuries. Then we're going to take that out, uncap the needle, withdraw a larger volume. Let's say we started at 0.5 of a milliliter. We're going to draw up so that the total volume is 1 milliliter. And we use water for injection, not anything else. We take a reading. We then dilute it to 2 milliliters and take a reading. Then we dilute it to 3 and 4 and 5 and 6, 7, 8, 9, 10. And in every case, we take a reading. Now, think about what we're doing. We are changing the geometry of that liquid from a very small column, maybe a half a centimeter tall, up to 8 or 10 centimeters. The geometry is changing dramatically. That calibrator better give you the same reading with a plus or minus 10%. Every one of the different volumes, regardless of the syringe size, even if it's a 30 cc syringe, still has to be the same. Let's take a look at a pictorial. This will give you a good idea. Over here on the left, I'm sorry. Over here on, over on the far left, first syringe, you'll see that the volume below that black plunger tip is 0.5 of a milliliter. And we took a reading. In the second syringe, we've diluted it to 1 milliliter. We take a reading. We have not changed the activity at all, just the height of the column of liquid. And in the next one, we're up to 2 milliliters and 3 and 4 and 5. And then I ran out of space. And so you can see that the geometry is changing dramatically as the volume goes up. Now, what do we expect the reading to do? Go up or down? I would expect it to go down, because the more liquid you have there, the more it's going to attenuate the photons from technetium, and it's going to slightly lower the reading. It just can't lower it by even 10%. So let's take a look at a test and see if you think this is pass or a fail. Now you'll note the reading is slowly going down. And even if you compare the bottom, 24.5, to the top, 25.5, that's only a change of 1 unit out of 25. That's only a 4% difference. So that is another example of a pass. All the ones I've showed you have been passes, every single one. And so you'll need to take the volume up higher than that, but that's all I could fit in that pictorial, and that's all I put in the chart. It's a 60 cc syringe. There are rare occasions you need something that large. You need to check it for like 5, 10, 15, 20, maybe up to 40, something of that sort. Okay. I know you know the answer to this question. What are the limits for all dose calibrator tests?
10.
Sure, 10%. Plus or minus 10. Remember, if you go below minus 10 or plus or higher than plus 10, they're both equally bad. It doesn't matter whether you're too high or too low, but your obligations have changed. Many years ago, when you had a dose calibrator that failed, you had to contact the NRC and said, we have a failure. You don't have a reporting requirement anymore, but you have to send that calibrator back and have it repaired. And just the shipping back and forth with FedEx Priority 1 costs somewhere between $700 and $1,000 just to ship it. And it's going to cost a couple of $1,000 to repair it. So it's a pretty expensive venture to get that calibrator back into shape. And so every department should have a backup calibrator. We have 2 of them. We check both of them every single day. And that way, if one of ours fails, we have a backup. Now, our main calibrator is 20-something years old, and we have never had a repair to it. They are very reliable, very stable instruments, and we rely on them every single day to maintain patient safety for radiation doses. Okay, any questions about dose calibrators before we take a look at some wet chemistry stuff? Anyone? Any dose calibrator questions? Okay, let's take a little bit of wet chemistry here. There are 3 categories of impurities that we have to deal with regarding quality control. Number 1, there is a radionuclide impurity. There are numerous examples, but perhaps the best one is that when we elute the generator, we want technetium. We do not want molybdenum. Molybdenum is a radionuclide impurity. We don't care what chemical form it's in. We don't want it, period. And why don't we want it? For two reasons. The energies of the photons are between 700 and 800 keV. You're going to get septal penetration. They're going to go right through the collimator and impact image quality, guaranteed to decrease image quality. And they will also increase radiation dose to the patient because it's both a beta and a gamma emitter. So we don't ever want a radionuclide impurity. Another example might be in the strontium rubidium generator. You might have some strontium 82 parent there. We don't want that either. That's also a radionuclide impurity. Next category is a radiochemical impurity. The implication is we have the right isotope, that is technetium, but here you can see HRTC, that is hydrolyzed reduced technetium. Your exam question might be, what's the physical form of hydrolyzed reduced? And it is a colloidal suspension. It's a suspension of very tiny particles that will eventually settle, but take hours to do so. And we don't want a colloid because where is it going to go? You know, colloids are liver spleen agents. So if you have hydrolyzed reduced contaminating your bone agent, you're going to get a liver spleen bone scan. That's not what you want. So we don't want hydrolyzed reduced technetium. That is a radiochemical impurity. It will impact radiation dose, and depending on what the impurity it is, it will and most likely will affect the image quality. Finally, there's a chemical impurity. The only good example I can give you today is aluminum ion breakthrough in the generator. Where did that come from? There's aluminum oxide in the column. Under some conditions, especially low pH, which we really should never have, but if we do, it could solubilize some of the aluminum. And we're not worried about the patient's safety. People swallow hundreds of milligrams of aluminum every time they take Maalox or Mylanta. We're concerned about aluminum ion because it interferes with red cell labeling, sulfur colloid labeling, and especially bone agent labeling. So we just don't want it there. And lucky for you, we no longer have to perform that test because back in 2011, the NRC said it's totally optional. You're no longer mandatory to do it. And it will also impact the image quality. Now, let's take a look at how we detect these impurities. For radionuclide impurity, like molybdenum, I think you're all aware that what we routinely do is to use the dose calibrator, but a much more high resolution way of detecting radionuclide impurities is with an MCA. Multi-channel analyzer generates a gamma ray spectrum. We can look at the peaks and look at the energies and look it up in a book and say, oh, that looks like molybdenum 99. I can see the photon energies of 740 and 780. Now, we don't do that on a routine basis because, number one, an MCA costs about $40,000. You have to replenish the liquid nitrogen supply every single week because it boils away, and the crystal only works at liquid nitrogen temperature, and there's a big learning curve on it, and there's no need to do it. If you have an isotope that's contaminating and you don't know what the isotope is, then you need it. But to check routinely for molybdenum, dose calibrator is fine. Secondly, there are radiochemical impurities, and today, what we use is thin layer chromatography, or we might even use paper chromatography. And you probably have seen the chromatography strips that are used in the hot lab. They're small. They're about 6 centimeters tall and maybe 7 or 8 millimeters wide. And we elute them with a liquid, with a solvent, and they migrate very rapidly. In fact, they're often called ITLC for instant thin layer chromatography strips because they take a minute or two to elute, and then we're going to cut them in half and count the halves and do the calculation. We're actually going to do that shortly. And finally, there is one chemical impurity, the aluminum ion, that we used to have to deal with. And I'm going to show you how we do that test anyway, just in case it shows up. I doubt that it will. It shouldn't. It's not a mandatory test, but you never know. So first, let's talk about the Molly breakthrough test. First of all, What are the upper limits of permissible moly breakthrough? Which choice do you like? 1 or 2 or 3 or 4?
2.
Sure. If I were the NRC, I would never have chosen that. It's 0.15 of the microcurie per millicurie at the time of administration. That means that since molybdenum and technetium are decaying all day long, that ratio is going to change. And so it has to be calculated for every single technetium patient. Now, fortunately, we humans don't do that. The computer does it for us, so we don't really care too much anymore. But in the good old days, we would have had to calculate it. So it would make more sense to me to do it at the time of elution. You do it one time. If it passes, you're done for the day. But that's not the law. It's at the time of administration, and that is computed all day long. That's the only correct answer on that whole slide. Aluminum ion breakthrough, hopefully they won't ask you that, but the correct answer is 10 parts per million. And here are the NRC rules. Moly breakthrough, 0.15 microcurie per millicurie. And remember, you only have to do it once. If it passes on the first elution, you're done for the week. You don't have to do it again. Aluminum ion breakthrough, if you choose to do it, again, first elution. Now, what happens to the moly-tech ratio during the day? We know molybdenum and technetium are both decaying, but at totally different rates. The molybdenum is decaying slowly and the technetium is decaying rapidly. What happens to that ratio? Does it go up or down? Remember that molybdenum is decaying slowly, technetium is decaying rapidly. The denominator is going down faster than the numerator. What happens?
Increasing.
Yes, it will definitely increase. Every batch of technetium will eventually fail the moly breakthrough test, but it typically takes 40 or 50 or 60 or 80 hours to fail. All we care about is 12 hours because the legal limit for using pertechnetate is 12 hours. So all we care about is, can we get through one business day? After that, we just throw it away. It's garbage. You can't use it. We don't care about it. So that ratio is going to go up all day long. And so if it ever does fail, the computer would let you know. Now, let's talk about how we do the moly breakthrough test. Just a brief description, and then we'll look at a pictorial that will make it a little bit more clear. First, we take the vial of technetium. We put it in the special lead container that came with your dose calibrator. You can't borrow one from somebody else. It has to be that specific one because it's a specific number of half-value layers for molybdenum's energy. So you put the vial in there, put the lead cover on the lead container, put it in the calibrator, take a reading on the moly setting. Then you're going to take it out of there with long-handled tongues, put that vial into the very thin but very strong plastic sleeve, put that in the calibrator, check it on the technetium setting. And you're going to look at the bottom of the slide, going to take the microcuries of moly and divide it by the millicuries of technetium and obtain a ratio. You must record a ratio. You don't have to worry about that today because the computer does it for you. So here's the pictorial. On the left, you can see the vial inside that special lead container, and the little curved handles assure that when you put that into the calibrator, it goes to the same depth every single time, same geometry. Take it out of there with the long handled tongs, put it in that plastic sleeve. It's like a 1/100th of an inch thick. It's a very strong, but very thin plastic sleeve, basically 0 half-value layers for any isotope. We take a reading. So then we will take the microcuries of molybdenum, divide by the millicuries of technetium, and we come up with the ratio. Now, what about this? What if you did it in the reverse order? Let's go back to that diagram. You did it in the plastic sleeve first, and you got your technetium reading. Then you did it second in the special lead container, you got your moly reading. And here's your question. Does it make a difference? And the answer is yes, it does. When you put a large amount of technetium from a generator let's say 1 or 3 or 5 curies, it leaves a huge charge on the ionization chamber. It takes literally 2 to 5 minutes for that charge to dissipate. We're not waiting 2 to 5 minutes, we're waiting 10 seconds. So if you do it in reverse order, the likelihood of failure is probably over 90%. You must do the moly first and the technetium second. And as a rule of thumb, it's just a calculation I did. If it's below 0.038, it will take at least 12 hours to get up to the limit of 0.15. So that's just a good rule of thumb. It's not anything legal at all, but just a calculation I did. Just as an inspection issue, the inspectors want to see a ratio. They don't want you to eyeball the numbers and say it looks like a pass. They want to know the ratio. And today you don't have to worry about that because your inspector, your computer always calculates that ratio for you. Okay, let's take a quick look at radiochemical impurities in technetium pharmaceuticals. There is Freetec. What's the difference between Freetec and pertechnetate? Nothing. Freetec is pertechnetate, but we use that term when the pertechnetate or the technetium is broken off of our molecule and formed Freetec. Let's say you made technetium MDP and it dissociated and formed some pertechnetate TCO4 minus. That we call Freetec. It is dissociated from the molecule. We don't want it. Where does Freetec or pertechnetate go? It goes to the choroid plexus in the brain, salivary glands, the thyroid, the gastric mucosa. We don't want it. Also, I mentioned earlier, hydrolyzed reduced technetium. The chemical form is probably a hydrated technetium oxide. That's not important. What is important is you know that hydrolyzed reduced is a colloid, and you don't want it because it's going to go to the reticuloendothelial system, including, of course, the liver and the spleen. Now, for these different pharmaceuticals that are shown here, DTPA, MDP, glucoheptanate, pyrophosphate, hydroxymethylene diphosphate, MAA, and sulfur colloid. They all use pretty much the same system. So the first system is silica gel strips eluted with saline. And the second system is paper acetone. That's what almost everybody uses. And that helps to identify Freetec. And you'll see a diagram that'll make this clear in just a moment. The way this works is that these systems separate one impurity on a certain half of the strip, and everything else migrates to the other half. So in the first system here, for example, if hydrolyzed reduced tech is on the bottom, we would take the counts on the bottom and then divide by the counts on the entire strip, and that'll give us a percent hydrolyzed reduced. The bottom one, Freetec, goes to the top, and everything else stays at the bottom. So we would take counts on the top half, divided by counts on the total strip, and that'll give us a percent Freetec. We're going to do the calculation shortly. You won't need a calculator to do it. Now, for insoluble things like MAA and sulfur colloid, they don't migrate in any strip. So we have no way to separate hydrolyzed reduced from anything insoluble. So we have no way to test for it, and we don't. This is what a strip looks like. It's about 6 centimeters long, maybe 7 or 8 millimeters wide. And the most important points are this bottom line here. The one is a little too high on the chart, but the bottom line is the origin where we spotted the strip. There's a cut line, and then there's a solvent front. So we put the strip in the tank with about 1 milliliter of the solvent. The solvent climbs up the strip, affects the separation. When the solvent reaches the solvent front line, we pull the strip out and immediately cut it on the cut line. The cut line is not always in the center, but usually it is. So the calculation is pretty simple. The percent impurity is the counts on the half of the strip containing the impurity divided by the counts on the whole strip. And then to get the labeling efficiency, we simply say it's going to be 100% minus the sum of all of the impurities. So show you a little calculation. Let's say that you have MDP. let's say it's contaminated with a small amount of hydrolyzed reduced, a small amount of free tech. So you can see that the hydrolyzed reduced, the 2 arrows are going toward the bottom. It doesn't migrate in any system. Free tech happens to migrate in both of those to the top. So what really matters is what happened to the MDP. In the acetone, which is a non-polar solvent, MDP doesn't migrate, so it stays at the bottom. But in saline, MDP migrates to the top. So look what we've done. On the left-hand strip, we have free tech on the top and everything else at the bottom. On the right-hand strip, we have hydrolyzed reduced at the bottom and everything else on the top. So let's see if you can do this calculation for me. Sorry, whoops. So if we have on the left, if we have 1,000 counts associated with free tech and 99,000 counts associated with everything else, what's the percent free tech on that left strip? Remember, it's the part over the whole. It's the top number divided by the total. Anybody? So it's going to be 1,000 divided by 100,000. What percent would that be? 1 divided by 100 is?
1.
1%. And on the other strip, we have 1,000 at the bottom, 99,000 on the top. That'll be 1,000, again, divided by 100,000, 1%. So if the, here's your math on the top. You can see that free tech and hydrolyzed both are 1%. So the labeling efficiency, and this is a calculation your computer is doing for you, will be 100% minus 1 plus 1 minus 2, 98%. 98% is MDP, 1% is hydrolyzed reduced, 1% is free tech. It is possible that you could get that calculation on your exam. I would not be the least bit surprised. I don't know that it's a question, but certainly could be. Okay, any questions about that? Okay, we have one more thing to cover, and it's going to take about 3 minutes, and we will finish right on time, and that is aluminum ion breakthrough. This may be a total waste of time, but they should not be asking you about this, but one never knows. So here's what we're doing. We want to use what is called a colorimetric test. Now, even though I'm a little colorblind, I can do this test, so I'm sure you can also. We have a test strip. It's about 1 inch long, 1/2 inch wide. On one end of the strip, we put a drop of eluate from the generator. On the other end of the strip, we put an equal size drop of a standard, an aluminum ion standard. That's a component part of the kit. And it is at the legal limit of 10 parts per million aluminum. This is a very sensitive test. So here's what this test would look like. We've spotted the eluate on the left side. We have the aluminum standard on the right. And this is a pass-fail test. We don't try to quantitate it. We don't look at that pink color and say, oh, it looks like a 4.6. It's pass-fail. And here's how easy it is to interpret. If the generator eluate spot is less red than the standard, it's a pass. It's literally that simple. So that is certainly a pass because that pink color is pink, certainly not white at all. Okay, and let me turn off the screen sharing. Okay, and we're done for today. I will still be in Florida next week, so be in a different hotel or somewhere, but we'll be meeting again same time next week, 9 o'clock, your 9 o'clock Central Time as always. Any questions from anyone about anything we have covered? Okay, great. If not, as always, thank you for your attention and looking forward to seeing you next week, and have a great week.
Thank you.
Thank you.
Bye-bye. See you next week.